right, why don't we go ahead and get started? So welcome back everybody to EE290C. So just a few administrative things before we get going. So I'll be actually out of town this Thursday, and since I think we're actually doing pretty well in terms of material, I decided to just go ahead and cancel that lecture. So there won't be any sort of makeup or anything like that. You know, I promise we'll cover all the same material later on. So you're just off this Thursday. I'll also be out, out of the office. I won't have the office hours that day. But as usual, if anybody has questions or anything like that, feel free to just send me a note and we can talk over email. So I'll be posting the second homework probably later on tonight. It'll probably cover the material, obviously, from sort of equalization and stuff and timing that we talked about last week, and probably some of the stuff that we'll talk about today in terms of link budgeting or performance analysis. And then the last thing I wanted to do was, I sort of kind of quickly went through the homework number ones that people turned in. I'll be posting the solutions hopefully also maybe tonight or worst case tomorrow or something like that. But there's a couple things that I sort of noticed that maybe I'll kind of briefly cover. But before I do that, were there any questions from you guys in terms of homework number one, in terms of just how to approach the problems or things that didn't make sense or anything like that? Yeah.
Around that static power consumption?
Okay. So I'm guessing that your question is related to, I believe it was problem number 2A or something like that about, the termination. And right, okay. So that's actually exactly the one that I wanted to review because it looked like actually a few people, I think just about everybody, a few people tried to get around the static power. Unfortunately, I don't think it quite would have worked. But even the ones that did it sort of, let's say, correctly, a few people seem to have calculated the static power slightly not correctly, so I wanted to actually walk through that one in particular. Okay, so the way that problem was set up was basically you had your transmitter, which I said was basically an inverter. And then I said that there was some, termination resistance in series with that inverter. And then, of course, there was a transmission line. And then over here, for my receiver, again, I just used an inverter. But I said that the switching threshold for that inverter was supposed to be VDD over 2. Okay? So the trick was that you had to add in a termination, but still keep that inverter sort of at a nice, good bias point. So I don't remember if I saw this, but there was maybe one or two people that, tried to just terminate it by doing essentially that. Okay, so now maybe somebody here, you guys want to tell me what's wrong with just doing exactly what I drew there? Yeah. Oh, okay. Well, so actually, I didn't even draw that. So you said something about you have to pass a lot of current through it to get it to VDD over 2. I actually didn't even think of that. I guess you could do that. So in theory, you could do something like, add a current source right there and try and make the nominal bias point VDD over 2. So the ones that I don't think anybody actually tried to do that. The ones that I did see just sort of did this. And then if you just do this, if you sort of think about it, the swing for this particular configuration, right, when this inverter is outputting a 0, meaning it's putting ground right here, then of course you're just going to get 0 volts right there, right? And when that inverter is, trying to output VDD, well, you just have VDD in series with RT, and then on the other side you have RT to ground. So of course that just means that you're going to get VDD over 2 on the other side, right? Now that's sort of bad news because that was just barely the switching threshold, right? So instead you'd like to place the swing sort of centered around that VDD over 2 point, right? So there's a couple of different ways you sort of could do that, but the most straightforward way, at least the one that I was thinking of, was doing something like that. Okay, so basically, if I look into this point, you're still going to get equivalently an RT of resistance, because you just have the two RTs in parallel, right? But now, just by sort of rearranging things, I've at least placed the nominal bias point at VDD over 2, right? Does this make sense to people, or? Okay. So now, there was a couple of people that I think maybe sort of tried to do something to try and get rid of the sort of static DC current. So I think one of the proposed solutions that I saw was something that looked sort of like this. So they said RT over here and then something like C big like this. Okay? So this kind of looks temptingly close to working. But it turns out if you think about it a little bit more carefully, it doesn't exactly, really get rid of the problem in terms of the power consumption. So does anybody want to explain to me sort of, maybe what's the issue with this in terms of why it doesn't really get rid of the amount of power you'd have to spend, or why it really doesn't change the power? Yeah. Okay, so you said you're still charging it as charging a capacitor. That's true, but that's, I think there's an easier way to explain it. So you're right, there is going to be some voltage swing on that cap. If you work out the sort of charge pulled on and off of that cap, it will be the same as it was before, but there's, let's say, a little bit easier way of explaining it. So if you did something like this, what was sort of your intent for that network to look like at any frequency of interest? What is it supposed to look like? Yeah, it's just supposed to look like a resistor to ground, right? Okay, well, guess what? If at any frequency of interest it looks like a resistor to ground, your current is going to be set by that voltage over the resistance to ground, right? So the capacitor maybe was a good trick for creating the... Oh, oops, let me change that to a different color. The capacitor here was maybe a good trick for, not tying it to another power supply, per se. But in terms of the sort of current you'd have to spend to develop the signal you're interested in, you'd still have to just drive that current into that RT, okay? Now, it does turn out that maybe you can get a slightly different power number. If you guys are interested, we can sort of walk through that. But basically, don't forget, if I'm going to be terminating things on both sides, whether you like it or not, you're going to have to dealing with sort of 25 ohm impedances, and not with, sort of some magic 50 ohm somewhere, or even infinite at DC, because, the signal has an AC component to it, and so I have to develop that magnitude at AC. Is there a question in the back, or? Yeah, so that's what I was going to say, is we can actually walk through it and sort of see, what this power would be in comparison to that power. But actually, on that note, I wanted to walk through and sort of do the calculation of what this power is, because I saw also a couple of, let's say, issues in terms of doing that correctly. Okay? Yeah.
Suppose you have a stream of, so you have a DC signal coming in, a stream of...
Okay, so if you have a DC signal, is this going to work? Like, is this type of system going to work correctly?
Well, this was... You had another resistor divider, but had larger resistors in series in parallel with that.
Okay.
So that guy still sets your.
Well, so let's just do one thing. Even if I do the resistor dividers, I think that's still not going to help you, because let's just do one thing. So let's say I had a long DC string of ones, right? So that I just have VDD for a long, long time there, right? Okay. When this transitions from a 1 to 0, how much voltage swing are you going to get right here? Just what's the magnitude of that swing?
You get about half of that, right?
Yeah, you get VDD over 2,
yeah.
Right? Okay, so if I get VDD over 2 of swing, and let's just say I just do one pulse like that, well, guess what? I haven't even crossed the threshold, right? Because the problem is that because you aren't DC terminated, you can kind of think of it like creating ISI. Right? You can kind of think of it as like your whole signal is getting shifted off away from the switching threshold. And then since you only have the same swing as you would have had before because of this termination, you would basically create an error if you let it last for too long on DC. So if you were to actually do something like this, meaning do this like AC termination structure, you'd have to make sure that you don't have too long of a run of like constant 1s or constant 0s, because if you did, you'd actually get a mistake. And by the way, adding a big, let's say to some V bias over here wouldn't really fix it, because that big resistance is so big compared to 50 ohms that it's just overpowered, right? Does that make sense? Or? So by the way, don't let me discourage you from, you guys trying to find clever solutions. Just sometimes they don't quite exactly work out. Okay, so let's actually sort of see how much power, let's say the design that at least I was thinking of would end up dissipating, at least from the sort of I squared, or let's say from the V times I, or the DC current flowing through those resistors. Okay? So let's just sort of look at two situations. So let's say that the TX is outputting 1 volt. Okay? Meaning, of course, before the termination resistor. Okay? So if I wanted to figure out the total amount of current flowing through the VDD, and let's assume that the VDD on the transmitter is the same as the VDD on the receiver over here, what would be kind of like the equivalent model for that? What would that look like? Just including both the transmitter and the receiver. And again, with this particular termination structure up here.
So I have a resistor from VDD to the middle of that point.
Okay, and what's the value of that resistor?
50.
Okay, that's RT, or let's just call it 50 ohms, right? Okay, then you hook it up to the resistive divider, right? And that resistive divider was 100 ohms here, and 100 ohms there, right? Okay, so now, how much current is flowing from VDD to ground? Or just how would you calculate it?
The equivalent resistance and then V
Right.
over R.
So it's the equivalent resistance, which is going to be 50 ohms in parallel with 100 ohms plus 100 ohms, right? Is going to be the sort of equivalent resistance there, right? So that turns out to be 133 ohms, okay? So now, by the way, even if you're outputting a 0, the model is quote-unquote the same. It's just that now I've just got something like 50 ohms here to ground, 100 ohms there to ground, and 100 ohms up to VDD, right? But notice the total resistance between VDD and ground is still going to be the same as it was before, right? So it turned out let's say the right answer in terms of how much current this was, it ends up being 1 volt over 133 ohms, which gives you 7.5 milliamps, okay? So there's a few people that I saw that I think got like 5 milliamps or something like that. You know, I haven't deconvolved yet where that came from, but I just wanted to kind of quickly run through this one because, you know, I just wanted to make sure that it was clear sort of how you draw these models to make sure you get the right answer in terms of static current. Does this make sense to everybody, or? I guess maybe somebody who didn't quite get it, you know, have any, just to make sure that it's clear. Any questions, or?
Well, I didn't use this. I was using the AC topology, but
okay.
if you your question, I believe, asked how much power is being consumed by the driver. So
Yeah. So now, if you treated it as, you know, just the power supply that's on the transmitter, I'll deconvolve what exactly that means. You know, there's a factor of 2 there that you'd have to scale by something, and, you know, slightly more complicated, but I'll deconvolve what that means. Actually, although even that, you know, I guess it all depends on how exactly you interpreted it, because you'd have to interpret it as how much power was pulled out of the VDD at the transmitter to exactly get that. Because if it was the power that was actually dissipated at the transmitter, then, you know, even when I'm pulling down to ground, there's actually power being dissipated on the transmit side. But, you know, don't worry, I'll try and deconvolve what exactly you were thinking of and see what the right answer is, and, you know, give you the appropriate credit for that. Okay, great. Other questions on this, or? Okay, so like I said, I'll go through the homeworks and do the grading and stuff. Hopefully I'll get you guys that back maybe in the next week or so. And also I'll be posting the solutions fairly soon, so definitely take a look, make sure that sort of things all make sense to you there, because obviously we'll be building upon the things that we're doing as we go forward in the class.
So this is only the static power, right? You haven't.
Yeah, this is only the static power. I haven't done anything with dynamic and, you know, anything like that. I was just, you know, I think most people did the dynamic part actually correct. I just saw a couple of people that, you know, maybe didn't quite get this one right. Okay, so, yeah.
I think if you separate the power consumption from transmitter and receiver, then you will get the 5 milliwatts.
Well, so now is again where we have to be tricky, because in terms of the total current flowing through VDD, there's going to be a total of 7.5 milliamps average. Now, what may indeed happen is that, you know, depending upon the data pattern, there's, let's say, 5 at the transmitter and 2.5 at the receiver or something like that. Like I said, I haven't deconvolved that yet. That's entirely possible. If that's correct, you know, like I said, I'll go and give you the appropriate credit. Yeah. Okay, great. So unless there's more questions on this, let's actually, you know, go back to where we left off last time. And so where we were last time was basically talking about equalization techniques. And we were almost done with this, and we were basically just sort of finishing up by saying that, you know, we talked about kind of continuous time linear equalizers, then we talked about sort of FIR equalizers, and we said that in both of them, the issue you run into is that essentially, at some point, you're going to be enhancing the so-called fundamental thermal noise. And then the final thing we sort of looked at, we said, well, if I want to get around that issue of enhancing the noise, then what I can do is use what's called a decision feedback equalizer, where the idea in the decision feedback equalizer was, once you've decided what the data actually is, you also will then know what all of the following ISI actually is. So if you know what it is, you can go and just directly subtract it out. And as long as you got the data correct, there's really no noise in your estimate of the data. And so you've basically gotten rid of that issue of so-called noise enhancement. Okay? So we said obviously there's a few issues with really doing this. First of all is that you can only really do this with so-called post-cursor ISI, because obviously you need to know what the data is first in order to then cancel out the ISI afterwards. And if it's precursor, then you haven't even actually made the decision yet, right? So nothing really you can do about that. The other was that we mentioned, well, if I ever make a mistake, then what I'm actually going to do is make the ISI even worse than it used to be, right? And so there's this issue of so-called error propagation where if the ISI is bad enough and you ever make a mistake, you'll just keep on making mistakes over and over and over again. Okay, but we said that's probably not too big of a deal in sort of the high-speed link context, just because we tend to operate at very, very low error rates in any case. Okay. The other thing that we sort of started to touch upon at the end was just saying that if I really think about building this thing, then I actually have a pretty substantial challenge in the sense that I have to build this comparator so that it'll resolve some small analog signal, regenerate it up to a full digital signal, sort of scale it by this analog weight right here, then subtract it off from that analog node and get that value to settle all within sort of 1 bit time, right? So if you think about, let's say, a 10, 20 gigabit per second link, that means you have maybe 50 to 100 picoseconds to do that entire operation, right? So if you look at, a lot of papers about DFEs, they all talk about just how do you actually close that first very tight timing loop, okay? And indeed, it's very challenging. We'll actually talk some more about that a little bit later on. Yeah?
So if your ISI is good enough that you're not usually making errors, then I guess it's...
Oh, I think I know what you're about to ask.
Why do you need this if you're already
so
that good?
Saying that we operate at low error rates does not mean that if you did not cancel the ISI that you wouldn't have very bad error rates. Right? So I realize this is somewhat of a recursive argument, and indeed it is recursive. But basically the whole point is that let's assume the DFE worked correctly so that I really canceled that ISI. So if I really canceled that ISI and I have a very, very small error rate, then the chance of me making another mistake afterwards is still also very small, even though that chance is going to be much higher than it would have been if I correctly canceled that particular tap. Does that make sense? Or? Okay.
In other words, you sort of need to bootstrap it off of some known training sequence, right?
Well, not necessarily. So let's say it all depends on how bad things are to begin with, right? So it's indeed the case that if you just absolutely never got a correct thing in here to begin with, then of course it's never going to work, right? But the trick is that, or rather I should say, usually the way these things work is that you have some training sequence, and during that period of time you probably don't care so much about what the correct data actually was, right? And then as long as you get enough correct things flowing through the thing, so that by the time you sort of lock, now you have a very good chance of actually getting the right answer, right? Then once you're really receiving quote-unquote real data, then you're in reasonably good shape, right? Now, so that is indeed true that, at the very beginning of the world, so to speak, there's going to be some period of time where things are not going to be so good, right? Where you indeed may be getting some pretty bad errors and, it may not be clearing itself out for some period of time. So did I manage to convince you or not yet?
Why is the likelihood of making a second error small?
Okay. So that's actually something we're going to talk about in detail, or actually in more detail in this lecture today. But it really has to do with the details of the ISI distribution, right? So if you sort of think about it, if I have 1 bit in error, let's just assume I make that one mistake, right? Then on the very next symbol, that 1 bit is going to go through whatever the sort of, whatever that first ISI magnitude is. And instead of getting that right, obviously it's going to make that twice as bad as it was before. Now, if that's really, really bad, then indeed you're likely to make another mistake, and then you might indeed actually get stuck. But even if you do this, let's say your error rate goes from 10 to the minus 15 to 10 to the minus 9, or 10 to the minus 4, or even 10 to the minus 3, right? Well, even if it's 10 to the minus 3, still, 999 times out of 1,000, that next bit is going to be the right answer, right? And so that it'll just mean that that one bad bit will sort of propagate through, and maybe my bit error rate, for the next n samples will be worse than it would have been. But the probability of me making another mistake at that point may still actually be not that bad. Right? In other words, it may be something like 10 to the minus 3 times 10 to the minus 15 in terms of getting 2 successive wrong bits.
So the first post cursor is not typically huge compared to the other post cursors?
Well, so it really depends on the channel. So in link channels, and I'll sort of draw this a little bit later on, but actually we've even seen them here. It is indeed the case that that first post cursor tends to be large compared to the other ones. But it is pretty rare for that first post cursor to be so large that if you got that one wrong, that you're absolutely guaranteed to make another mistake. That's kind of the trick. Now, if it is really, really big, then indeed, right, like let's say that first post cursor was as large as the cursor itself, then yeah, if you make a mistake, next bit's going to be wrong, you're hosed anyways, right? Now, this is also where, let's say, things get, let's say, more interesting, in that I could have a random data pattern where it just so happens that even if I make this next mistake, at some point, I'll get back the right data afterwards, just because randomly the ISI added in a way that helped me rather than hurt me, right? Could happen. And then I may get back into a sort of a so-called good situation. So the interesting question there really becomes, at the system level, can you deal with a burst of errors that then may correct itself after some time? Or do you really need to just know that that one bit was an error and then you can correct just that one bit? So in most link systems, the way they're built, because they operate at such low error rates, if they do ever find an error, they'll just sort of throw up their hands and say, okay, just retransmit the entire packet, right? Because they may not have something built in to really tell you exactly where that error actually happened and how to correct it and things like that. But these are all great questions. Other questions on this? Or? Okay, so just in case you thought that wasn't, sort of complicated enough, it turns out that actually there's some even more, let's say, fun that you can have when you start thinking about DFEs. And that fun is that basically, I said a second ago that I would like this whole loop here to settle within 1 bit time, but I actually lied sort of slightly, okay? So if you sort of think about it, you remember that I'm going to be recovering my clock based off of looking when my data, transitioned across the 0 point, right? Because I was going to use that to sort of decide am I early or late in terms of sampling. Well, if you sort of think about it, if I have this DFE thing and then I take, that other sampler over here that's clocked half of the bit time away, then what I actually want is not only for this, correction to settle by that next bit time, I actually want it to sort of somehow magically not have any ISI left when I actually do that edge sample, right? So now if you think about it, my constraint actually has something involving like half of a bit time in it, right? So now if I'm at 10 gigabits per second, now I need even 50 picoseconds to sort of settle something out correctly, okay? Now, this actually sort of gets really interesting in the sense that, if I look at my channel, then, the amount of ISI I have left at sort of half a symbol time away really won't be the same as the amount of ISI I have at the full symbol time away. And in fact, there's no necessary relationship between those two, right? It doesn't have to be the case that one is half of the other or anything like that, right? So in fact, if you really look at it, a lot of times what you have to even start thinking about is really having essentially a different coefficient in this feedback loop for the sample that actually gets sampled half a bit time away versus the sample that sampled a full bit time away, okay? Now, it turns out that this issue is actually not unique to DFEs. It actually happens even in the FIR transmitter or even in the FIR linear receive equalizer as well. And if you sort of remember, I said that, keep in mind what the pulse shape really looks like, because that can have an impact on the clock and data recovery. That's really kind of what I'm saying here. Okay, so the trick here is that basically if I have just an FIR filter, then it doesn't really, and I'm running it just at the symbol rate, it can't say anything about what the samples are outside of where, at the one sample point that you're really controlling, right? So in other words, you really can't control the pulse shape because that's kind of beyond the Nyquist bandwidth of your FIR filter, okay? So it turns out the only way really to fix that is to do what's called a fractional equalizer, or to do a so-called oversampled equalizer. Okay, so what this would mean is that let's say you were operating at 10 gigabits per second, you would have to build something like a 20 gigasamples per second equalizer so that you can then control those edge samples as well to make them also clean or free from the sort of intersymbol interference. Okay, so just to sort of show what this looks like, that's kind of so I've got this plot here of sort of the result of, let's say, a fractional versus a symbol rate equalizer. So just to sort of draw it and make sure it's clear, if I have a symbol rate filter, then what I'm basically saying is that if I take my input, right, I'm just going to be passing it through a full symbol of delay. And as we said before, there's going to be some W1 here, of course some W2 there, and then I add those two together, and that would be, for example, some 2-tap filter, right? If I actually need to do a fractional filter, where I'm oversampling, and I'm going to abuse notation here slightly. So let's say I wanted to do a fractional 2x oversampled filter. Then now what I would actually have to do would look something like the following. So I take my input, still scale it by some coefficient here, but now I'm going to delay it by a half symbol period. Right, so this is where I've sort of abused notation because I said z to the minus 0.5. I don't think that's technically the right way to do it, but you guys get my meaning, right? Okay, so now I have another weight over here. Let's call that W2. Again, I delay it by z to the minus 0.5. This is now, for example, W3. Delay it yet again. Let's say that's W4 here. And then, of course, I just add all these together to get my final output. Okay, so the whole trick here is that if I really do one of these fractional equalizers, then now what I can actually do is, because now I have sort of control over the sample points, not just at when I actually will do my final data decision, but at the edge locations as well, right? So as an example, if you sort of look at this picture here, what I've done, the blue is like if I did the symbol-spaced equalizer, but I just oversampled it at a factor of 2. Okay, so what you can kind of see is this blue pulse here, I just ran, basically in this case I believe it was an MMSE equalizer. Okay, and what you can see is that indeed I've got a nice clean sample at my symbol point, but half a symbol away right here, I've still got some ISI left, right? And half a symbol away on the other side, I've also still got some ISI left, right? So that would mean that even though my symbol samples would act, or my data samples would have no ISI on them, on the edges, you'd still see a lot of ISI, right? So you can imagine in terms of the clock and data recovery, and again, this is something we'll talk about some more today, having that ISI left over could substantially change the behavior of that clock and data recovery, okay? Whereas if I do this fractional equalizer, well, now I can actually specify that I really want these edge samples to be 0, right? So I could basically force it to say, okay, set your coefficients so that these two edge samples are also 0, so that you're not basically creating ISI on the edges when you're trying to recover what the clock actually is. Okay? Does this kind of make sense to people, or? Yeah.
Want to be 0 or 1/2 to be, because it's edge, right?
So what I assumed here was that the data was plus minus 1.
Oh, okay.
Meaning that you really want it to be 0 because the transition point is 0. Obviously, if it was single-ended, you'd want it to be 1/2.
Okay, yeah.
Yeah, it's a good question. Yeah.
So this whole thing is basically make sure your bit looks more like a perfect square?
So
Instead of
kind
a
of. It's not
triangle?
really going to look like a perfect square. It's just going to, if I actually drew this in time, it would probably look something sort of like this. It's just that, at the sample points, you'd try and make sure that even on the edge sample point, it's at 0. Right? Now, there's no way to make it, let's say, perfect. Or rather, if I wanted to make it perfect, then I'd have to oversample this even further. Right? Because I'd have to really control all the way out to whatever the Nyquist bandwidth of that pulse shape you're trying to create is. Okay? So by the way, people have talked a lot about these fractional equalizers and things like that, but I will tell you now, I have very rarely seen it actually used. So now, anybody tell me why is that? Why do you think it's not such a great thing to do?
It's really hard to make a symbol rate one, and this is twice as hard.
Okay, well that's fair. So you said it's hard to make the symbol rate one. This is like now twice as hard. turns out actually, we'll see a little bit later, the symbol rate one, at the transmitter is not so bad. That's pretty doable, but you're absolutely right. However bad that was, it's at least twice as bad, to do this, right? So that's certainly true. But let's maybe quantify the badness. So what badness are we going to pick up by doing this fractional equalizer? Let's do the obvious one first. If I just take something and run it twice as fast, what's going to happen? I think you said it.
Power goes up.
Yeah, power is going to go up, right? That's clearly the case, because I'm just going to have twice as many flip-flops. I'm clocking them all twice as fast. Guess what? That's immediately a 4x hit in power, right? At least on the flip-flop side, right? So that's certainly true. There's actually another, let's say, communications reason that this can turn out to be somewhat bad. I'll give you guys a hint. So what did we say was kind of the problem with equalizers in general when you had to sort of get rid of ISI, so to speak? For specifically at the transmitter, what was it you had to do to basically get rid of the ISI at the transmitter?
Throw away gain?
Yeah, you basically had to throw away DC gain, right? In other words, if I used to be transmitting something that looked like this, then now I have to be transmitting something that looks like this, right? Well, so now if I'm going to do a fractional equalizer, and I'm even going to make sure that, not just out to this bandwidth, but out to twice as far in terms of bandwidth, I'm flat. What am I going to have to do? Yeah, I'm going to have to throw away even more gain, right? So in other words, I'm basically just going to lose even more of my signal. Okay, so this is actually sort of a good segue into what we're going to talk about today.
But wait, that's in the context of the FIR implementation of the transmitter, right?
Yep.
But we said the DFE.
Ah, okay. So you're saying, what if I did a fractional DFE?
Yeah.
Yeah. So okay. So that's fair. You can indeed actually do that, but again, you've actually now doubled the amount of power you're spending on that fractional DFE. And by the way, you also still have that issue of resolving that signal, getting through this thing, and then making it to that edge comparator all within half a bit time.
But you don't get the
that's right. In terms of the noise enhancement, that's right that you don't take quite that penalty. Although when we really start talking about the circuits, you can imagine I sort of have now two completely separate DFE structures that I have to drive. So from a capacitive loading standpoint, I may actually have twice as much loading, have twice as much complexity, but you're right, at least from the noise enhancement standpoint, it's not quite as bad. So I should say, like I said, I don't think I've ever seen a commercial link really use this, but I believe if they were to use it, they'd probably use the fractional DFE before they used the fractional, linear equalizer. And again, we'll actually talk some more about, let's say, some of the trade-offs there. Turns out there's actually some other techniques that you can use to try and get around some of those issues. But we'll talk more about that later when we really get into the details of how you build the CDRs and what are some of the algorithms people use there. That's a great question. Other questions on this? Or? Yeah.
For fractional DFE, you need twice number of taps as a regular DFE, right?
That's right.
Okay.
Because each one of these taps would now have sort of the, each one of these would also have the fractional version, which might be a different value, right? Which of course you'd have to estimate separately because you don't necessarily know, there isn't necessarily a direct relationship between the main tap value and the fractional tap value.
That's actually equivalent to two DFEs with
That's
one
right.
for edge, one for the data.
That's right. There's basically two DFEs, one for the edge and one for the data. Charles, did you have a question?
Yeah, could you actually just move this whole thing to the transmitting side, meaning like do some pre-distortion after you characterize the channel? So in that way, you only need to do some latency. You don't have this timing.
Well, okay, so here's the trick. I don't know exactly how you build a transmitter that, how should I say this? Like, the whole trick is that there's going to be noise that I receive at the receiver over here, right? So I don't know how I build a transmitter that non-linearly subtracts the ISI.
You probably need an ADC in there, right? Probably a few bit resolution.
Well, remember, I'm at the transmitter, so I have the digital data.
You actually need a DAC. That's actually what I meant to say, yeah.
Right, but the transmitter is already a DAC. I'm okay with that. I'm only asking, it's not clear to me what the nonlinear processing that you can do before the channel is that wouldn't have sort of that wouldn't have, let's say, an impact on the noise that you see. That's not to say that there isn't any nonlinear coding you can do. There are some things out there that, sort of in the comm world that people have talked about, but I don't know of any of them that have sort of the same non-noise enhancement characteristics as the receiver does. And in particular, if you keep in mind that your transmitter always has a peak swing, any sort of processing that you do is basically going to eat into that peak swing. Right? In other words, the only thing you can do is not transmit the peak, but rather transmit something smaller.
Well,
Right.
you're not going to help you in terms of the noise performance, but you're going to help you in terms of power, because that thing potentially doesn't need to run at full speed, right? It doesn't need to run at this transmission speed. So you can probably
Well, eventually something has to run at the transmission speed. So you're right that I could do something where I have some parallel digital processing and... Well, right. So you're right that I could do some parallel processing and that at the end serialize it all onto the line. But at the end, I really have to get it all onto the line. Okay, and as we'll see maybe in about a week or so, when we talk about how you really build these things, at least in the last few years, for all of the designs that I myself have been involved in, if you looked at how much power, let's say, that DAC took versus how much the flip-flops and the digital logic in front of it took, the digital logic just for flops cost you more than the analog stuff did. Okay, so if you want to put a microprocessor there, I think unfortunately you'll be spending 100x more power than what I would just by doing this DFE. But it's a great question. Certainly there's a whole list of communication techniques people can apply. I've sort of focused on the ones that from a real practical implementation in terms of these links, so far people have found to be really, let's say, effective. But don't let me stop you. Feel free to explore other options. I'll just sort of give you the warnings as to what I've seen. It's a good question. Other questions? Okay, great. So unless there's more questions on this, let's actually go ahead and move into sort of the main topic for today. Okay, there we go. So the main topic for today, what I'd really like to sort of focus on, is actually sort of talking about link performance analysis. And to sort of clarify what I mean by that, we've talked a bit now about sort of what the basic transmitters and receivers looked like. We've talked about sort of what the overall environments look like. We then talked about sort of using equalization to try and counter the ISI. But turns out really figuring out sort of is my link going to work at the bit error rate I want it to is not quite as straightforward as a question as you may think it at first is. Okay? So this is kind of going to be the wrap-up of, let's say, the high-level discussion of what links look like and sort of how you go about designing them before we really dive into some more of the circuit details. But this is an important thing to keep in mind, because remember, at the end of the day, you're always going to have this sort of system-level trade-off of, do you build a fractional DFE? Or do you do some nonlinear transmit precoding? Or do some other weird thing? And, at the end of the day, you're going to have to evaluate, okay, what does this really buy me in terms of a bit error rate standpoint? And, of course, how much power does it cost to really implement that particular signal processing or whatever it is that you're interested in building? Okay? So, kind of on that note, just as maybe some further motivation as to why I need to give you a whole lecture on, how you do sort of link performance evaluation, I wanted to just sort of pose one question to you guys. So I started this class out, maybe 3-4 weeks ago by sort of saying that, okay, roughly speaking, if you wanted to figure out the bit error rate for some link, then you could just sort of take this equation here, which said something like the bit error rate was 1/2 times the complementary error function of the input amplitude minus the offset, divided by square root of 2 times the sigma of the thermal noise. Okay, so I guess my question to you guys is that enough? Does this now tell me everything about the performance of my link I ever might want to know? Or is there something missing?
ISI.
Okay, so you said it doesn't include ISI. That's absolutely right, or at least it doesn't directly include ISI.
Is it assuming perfect sampling?
Ah, okay, so this says absolutely nothing about timing. Right, so this is assuming that I'm always sampling at exactly the right spot. Right? So now, actually, I want to push you guys a little bit more. So you said this doesn't include ISI. So how would you include ISI? What do you have to do to include that? And by the way, this is somewhat of a trick question. So, I'll say that most likely I'll say that all of you are wrong. But, you shouldn't feel bad because that was that's the kind of the core topic of this lecture. So how do you include ISI?
You could try to find your worst case amplitude.
Ah, okay. You can find your worst case amplitude.
You look at the eye diagram.
Ah, look at it. What about the eye diagram?
It includes the ISI.
Okay, so I think what you're saying is probably equivalent to what Dan just said, although there could be actually a nuance there, which we'll talk about a little bit more. But you said something like, look at the eye diagram, you could say, well, okay, this point right here is kind of like the actual amplitude I got after the ISI, right? Something like that. So turns out both of what you guys just said is indeed what people did for a long time, and we'll cover that one first. But again, there's actually a slight nuance there that can get, let's say, more interesting that I think we'll get to before we break for today. Okay, so we said there's no ISI, there's no timing. Anything else that I'm missing?
The shape of the eye might also matter.
Okay. So you said something about the shape of the eye. It turns out that that actually has a direct interaction with this timing thing. Okay, for multiple reasons, which we'll talk about as we go through the lecture today. So that's another great reason. Any sort of other problems that you can think of that might stop my link from working correctly?
Some other noise rather than similar.
There we go. There's lots of other noise. Right, and I'll put noise in quotes because, to be technically correct, it's probably more like interference. But what other sources might there be? What else might screw you up?
Crosstalk.
Okay, there we go. There's crosstalk,
Supply noise.
supply noise, anything else?
Link coupling.
Link coupling, what do you mean?
One link bit might couple to another.
Oh, I think that's probably crosstalk,
Oh yeah.
right? There's one other thing that, all those hardcore analog, well, okay, maybe not too hardcore, but even in 240, we spent some time just talking about, there's a few different, let's say, external things that you tend to worry about. Supply rejection was one of them, and there's another rejection that gets thrown around very common.
Common mode rejection.
There we go, common mode, right? Turns out it's sometimes difficult to differentiate what's the difference between common mode and supply, but indeed those could be two independent sources of noise, okay? Or rather interference, to be more precise. So that's absolutely correct. There's all these sort of sources of so-called interference that I'm going to have to deal with. The shape of the eye could actually have an impact on what you really end up getting in terms of bit error rate. Of course, where you actually sample the eye has a big impact on things, right? In fact, just sort of what the timing jitter is has a big impact. And then finally, as we sort of started talking about, I haven't really directly said anything about ISI here, but even with ISI, it's not 100% obvious how exactly you should include that in terms of calculating your bit error rate. Okay, so let's actually just sort of go through and let's do this a little bit historically in terms of what people did in the past, and then we'll build to some of the more modern approaches that are slightly more accurate. So, question? Yeah.
So you don't typically include the supply noise or the crosstalk into your amplitude? Like, I guess you would have some sort of a way to build it in, right?
Okay. So we're going to talk about exactly that right now. So that's a great. So the question was, isn't there some way of including the supply noise and the crosstalk into the amplitude? Basically, yes, but it's going to touch upon, let's say, one key issue that I'm going to talk about through the rest of this. Okay. So let's say the classical approach that people were using maybe about 8 to 10 years ago or so, maybe even a little bit less than that, was basically to say, okay, look, I want this thing to be bulletproof. I just want it to work. Okay, and so especially if you looked in like computer systems, so like memory interfaces or even Ethernet and things like that, they basically said, okay, I want to make sure that, if I transmit bit A over here, it's bit A over there, kind of no matter what. Okay? So the target error rates that were very common over there were easily 10 to the minus 20 or lower. Okay? So in those cases, what people really did was they said, well, let me just always do a worst case analysis. Let me just figure out what's the worst possible thing I can do to this thing and still make sure it works. Okay? So the way people would typically do that was with what was called sort of a voltage/time or VT budget. Okay? This is very similar to like a link budget if you're familiar with kind of the wireless terminology for it. It's basically the same thing. It's just that it includes not only sort of the signal itself, like the voltage amplitude, but also the timing aspect. Okay? Now, there's one really key thing to keep in mind, actually, throughout all of this discussion that we're going to have today. So the key thing you have to keep in mind is that with all of these budgets, you really have to separate out what is true random noise, and by random I mean things like thermal noise or 1 over F, from the things that are actually quote-unquote deterministic error sources. Okay? Now, why is it that it's really important to do that? Why, how can you sort of get yourself into trouble if you don't keep track of those two? Yeah.
You have different distributions.
There we go. They have different distributions, right? So in fact, even if I'm doing this worst case analysis, right, if I have truly random noise, that means it's unbounded. That means that from whatever reason, you could just get completely unlucky and you should get 40 sigma of that random noise, right? But for a deterministic thing, even if I can calculate what its sigma is, and even if it's hard to predict, then usually those things are bounded, right? Usually those things have some peak-to-peak error that they could actually cause on you, right? So the trick is that even when you're doing this worst-case analysis, the way you would typically do it is you'd basically figure out, okay, let me take all of my deterministic error sources and just snap them to their worst-case values, right? Once I've figured all those out, I would indeed just subtract them off from my quote-unquote input amplitude, and then I would look at what's my remaining signal and compare that to my true unbounded random noise sources. Okay? So let's just actually sort of walk through an example of how you might go about doing something like that. Okay, so let's say I have my, just some fairly simple link here. In fact, something that you might have built back in 240. You basically have a transmitter, some continuous time linear equalizer at the receiver, and then of course you feed that into some comparator over here, and I'll just call this the voltage at the input of the comparator, and of course that gives you your output data bits. Okay? So let's first figure out how we're going to deal with ISI. Okay? Because that's going to be sort of, let's say, the first type of error source that we've spent a lot of time talking about and could have a pretty direct impact on sort of your overall performance. Okay, so just to be sure that everything is clear, again, I'm going to be assuming sort of differential, or really more correctly, bipolar signaling, meaning that your data is always equal to plus minus 1. Okay? So in order to figure out what the ISI sort of impact is going to be, what you really have to do is look at essentially what is the pulse response going into that comparator, right? So let's just draw something in as an example. So let's say the pulse response looks something like, I don't know, like this. Okay? And actually, let me draw it, slightly. Oh, didn't mean. Something like that. Okay? Just, you'll see why I did that in 1 second. Okay. So first of all, to figure out what the ISI is, you have to figure out what's actually the desired signal, right? You have to figure out, like, what is the real bit that you actually cared about. Okay? So if I just give you this continuous pulse response like this, how do you think you'd decide what the actual bit you cared about is? Like, procedurally, what do you think you're going to do? Where would you like your bit to be? Or where would you like to sample to get your data bit?
The highest point.
Yeah, you just want to find the highest point, right? So you would literally say, okay, let me find what is that highest point. Let's just call that h peak. And let me assume that my CDR magically locks me to that right point. Or if it's not CDR, whatever it is that I'm using to recover the clock. Okay? So, and by the way, that's probably not exactly correct, but, let's go with that for now. Okay? So once I've decided that's sort of my main symbol, right? Then now what I basically have to do is sample this response at bit time intervals, right? So as an example, 1 bit before, maybe I have this much ISI. 1 bit before that, I maybe have that much. 1 bit afterwards, maybe I have this much. 1 bit there, maybe here, and maybe I have another one over there. And then let's just pretend that the rest of them are all 0. Okay? Okay, so once I've done that, now if I'm going to do this again, worst case analysis, what am I going to say is sort of the quote-unquote margin or the quote-unquote amplitude of my signal that I actually have? How am I going to go about calculating that?
Minus the largest ISI.
Okay, so is it the peak minus the largest ISI? And by the way, this is the response to just 1 bit. All right, so this pulse response I've drawn here is just the response to 1 bit that I could have transmitted. So what's the worst possible thing that could happen to me?
Maximum minus the sum of the
Yeah, so you said that the worst thing that could possibly happen to me is that for each and every single one of these other bits that are transmitted around me, I just so happen to transmit them in a way that they take away from my signal amplitude here, right? So in other words, if I wanted to find sort of the, let's say, the impact of the ISI, and by the way, I should mention here that in this case, I'm basically saying the ISI is deterministic, meaning that it's bounded so that I should really just subtract off its worst case in the amplitude. Then the way you'd basically do that is you'd say that essentially the quote-unquote margin, and I'm going to use margin here, but that's equivalent to amplitude. In other words, that's just sort of like how much voltage away from the threshold do you have. That's just going to be whatever the peak sample is minus the sum over all taps that are not the main tap, meaning they're not that peak value, of whatever that ISI is, but with the absolute value. Okay? So again, I've done an absolute value there because basically I'm saying that even, and I guess I didn't draw it, but let me go ahead and draw it. For example, even if I had a tap that was negative like that, right? If I just so happen to transmit the opposite polarity of the bit, then even that could take away from my signal amplitude, right? So you really have to add the sort of the absolute value of the ISI taps in order to figure out what's kind of like the worst case impact of all of those things adding up together and taking away from your signal strength. Okay? Yeah.
If you consider that, do you really want somewhere at the peak voltage or you want somewhere else? Like the peak V margin or something?
Oh, okay. Well, so you are right that you could try and come up with some more sophisticated, clock recovery scheme that would somehow maximize the peak margin. But remember, and we'll talk about this more in 1 second, even if I could just so happen to place it just in the right spot, where I just, maximize the margin, if I have any jitter around it, that may or may not be actually still the right place to sit at. Okay, so by the way, the particularly relevant example for those of you guys who like wireless stuff is if you used a raised cosine filter to create your pulse. In time, that generally looks, something sort of like this. Right, and I didn't draw the rest of it, but obviously it kind of continues the same way, just mirrored on the other side. Well, raised cosine pulse, if you sample it at exactly the right spot, beautiful. My ISI samples are all 0. What happens the moment I get any jitter at all? I get tons of ISI, right? Because if I just shift off ever so slightly, for example, to the left, notice each and every single one of those sample points now all of a sudden has ISI on it. Okay, so again, this is actually something we're going to talk about a lot more. But what this is kind of getting at is that indeed you can come up with lots of, let's say, sophisticated criterion on what was really the best sample point that gives you the best voltage margin. But keep in mind, all of those are going to be modulated by when you actually sampled it, or really by what the distribution of your sampling is really going to end up being. So again, we'll talk about that a little bit more, but I guess there's maybe just the other practical issue of how you'd calculate what that is, or how you'd get to that spot. But again, we'll talk about that a little bit later.
I guess what I'm asking is, like when you overlay different symbols, this point won't be the lowest voltage, highest voltage margin, right? Because that will be the.
You're just saying you should maximize this.
Right, like when you look at the eye diagram, the peak isn't the peak of the symbol itself.
Right. So I think what you're basically saying is that. Well, okay, so there's two different things you could be saying. So one would be from, let's say, a communication standpoint, if I had an infinitely good algorithm, then I could find, in theory, what was the sort of sampling point that really maximized this margin. Right? That's one thing that, in theory, could be done. The other could be that, if I really built my clock and data recovery the way I've sort of told you already, I may not really actually be landing right there. I may be landing somewhere else. Right? That's also actually absolutely true. And again, we'll see sort of how to deal with that in 1 second. Or maybe not in 1 second, but later on in this lecture. Okay? Because in fact, even if I nominally landed there, again, I'm never going to be sampling always at that exact same spot. Right? And so depending upon where I sample, I'm actually going to get a different voltage margin. That's all great points. Other questions on this? Or okay, so that's, let's say, probably the most complicated one, so to speak. All right, so of course, if I have, let's say, I don't know, residual offset or something like that. right, then what I can do is, of course, just I'll take whatever that margin was, and then just subtract off that residual offset. And similarly, I can do the same thing with things like, let's say, whatever my supply noise was. And again, I'm treating the supply now here as a worst case kind of thing, because it's deterministic, right? Whatever, let's say, my common mode noise was, whatever, let's say, my crosstalk was, and so on and so forth, right? So basically, for each and every single one of these things, I just figure out what's the worst sort of condition that I can be hit with, and then just subtract that off, because I assume that for all these deterministic sources, I will indeed hit that worst case condition. Okay? Does this make sense to everybody, or? Okay, so now, just to sort of, what should hopefully be kind of a quick review of, let's say, 240. So we've talked about the amplitude side, but of course you need to know what the noise side is as well. And let's say the good and the bad news is that that's usually dominated by thermal or 1/f noise. Okay, so from that standpoint, let's again just sort of draw our model here. But this time I'm just going to add in, noise sources kind of at each, let's say, active component that I've added into this system. Okay, so let's say I'm going to have some noise here from the transmitter, some noise here at the input of the CTLE, and some noise here from the comparator. Okay? So if I wanted to figure out what the total noise going into the comparator is, what do I have to do to go about calculating that? And by the way, I want you to keep track of the fact that all of these are not just, okay, so let's assume that all of the noise sources themselves are white. But let's remember that, everything that you go through here actually has some filtering characteristics. So just procedurally, how would you go about calculating the total noise sigma at the input of the comparator for this particular situation here? Yeah.
The transfer function from each noise source to where you want it to be.
Okay, so what do you do to that transfer function to find its sort of net contribution?
Integrate square.
Yeah, there we go. So you integrate that transfer function squared from 0 to infinity times the spectral density of that noise, right? So let's just actually write that out. Again, this should really be sort of a review. So your total noise squared would be something like integral from 0 to infinity. So if I first wanted to know the contribution of the transmit noise, then that would be, for example, first filtered by the channel, right? Then filtered by the continuous time linear equalizer. And then finally, I'm again going to sort of slightly abuse things, but let's assume that the comparator has some filtering input referred in it as well. Take that transfer function squared, and of course then just multiply it by the spectral density of the transmit noise, right? Does this make sense to everybody, or? Okay, so just to make sure we're all on the same page, then, what would this equivalent thing be for the noise at the receiver? Just what series of, transfer functions do I have to go through there for VRX?
Same thing, but you just don't have the H of the channel.
Right, exactly. You just don't have the H of the channel, right? So of course, first you go through the CTLE, right? Then you go through the comparator, and then that's it. And you multiply it by, again, the spectral density of the receiver. Yeah.
What's H comparator?
Okay, so here, I just did this, and you'll see why I did it in 1 second. I just introduced this extra filtering term here, because in 1 second, and let me actually just write it out, I'm also going to add in the noise that's filtered from that V comparator here. Okay. And of course, this whole integral is versus df. I just added that filter in because if I didn't and I gave you a white noise source, it would integrate to infinity and you'd complain. So I just put that there just, so that last piece there would actually evaluate.
It's the filtering seen at the input of the comparator.
Yeah, you can kind of think of it as the input referred, filter of the comparator. As I said, I'm kind of abusing notation a little bit here. But, just treat it as, really this is here just for you to figure out what is the input referred sigma squared of that comparator noise. Does that make sense? Or?
Yeah.
So you could think of it maybe as sort of like the sampling aperture of the comparator or something like that. Okay? Okay, so that's actually kind of it, right? So indeed, once you've done this, then at least from the voltage standpoint, you could basically say that the bit error rate would be just 1/2 of that complementary error function times of that V margin divided by square root of 2 times that sigma n that we just calculated. Where again, that V margin is that worst case V margin that we calculated. Okay? So this all works, but as we've sort of hinted at a couple of times now, is really, let's say, only half of the picture, right? Because right now, so far, everything that we've done has been purely in the voltage domain. And I've said absolutely nothing about timing, right? So if I really want to do this right, I actually need to sort of repeat this whole procedure, not just for the voltage bit error rate, but for the timing bit error rate, right? So in other words, I have to figure out both sort of what's the quote-unquote amplitude of my timing signal, meaning just how much time do I have to actually do the sample correctly, and then how much noise do I have in the timing domain, which of course means how much jitter is there on my sampling, okay? So let's actually sort of take a closer look at that. So remember I said there was going to be these VT budgets. So we've done the voltage. Now we actually have to do the timing as well. Okay? So conceptually, there's still sort of the same important distinction we have to make here. So just like with voltage, where we said we have to split between the deterministic and bounded sources of error and the, let's say, random or unbounded sources of error, same thing in timing. Okay? Because in timing, just like in the voltage, you could have things that are truly unbounded, meaning they're due to thermal noise. And you can also have things that are just deterministic, for example, like supply, that just jitter your sampling thing around with some maximum peak-to-peak value. Okay? So just to give you a few, let's say, again, some more alphabet soup, just so if you hear it, you know what people are talking about. Usually the way this is sort of referred to specifically in time is people refer to things in terms of something J, where J just stands for jitter. So for example, total jitter is Tj. That's always decomposed into deterministic jitter, which is dj, plus random jitter, which is rj. Okay? And then sometimes people will sort of mix between RMS values and peak-to-peak values. Okay? So just to be specific, this dj here would be measured as a peak-to-peak value, right? And then every deterministic source, since you're treating it as being worst case, you'd add that in, okay, linearly, right? On the other hand, for random things, so again, these are things that are really due to things like thermal noise. Those would be RJ, or random jitter. Those should be treated as RMS. But when you sort of calculate this total jitter budget, what you should always do is take that RMS value and multiply it by however many number of sigma you need to get that bit error rate that you're targeting. Right? So as an example, if you wanted, let's say, 10 to the minus 12 bit error rate, then your sort of peak-to-peak RJ would be 14 times the RMS value, which is just plus minus 7 on each side. Does that make sense to people? I see a couple of slightly confused looks. So, okay, so I'll just go back to this picture here. So you remember how we basically said that, let's say that this was my sampling threshold in voltage, right? We said that if I added some random noise onto that, and I sort of drew the distribution on the side here, right, then what you're kind of interested in is, when does the distribution of that noise, or when does that noise, what's the probability of it being larger than your actual signal amplitude that you get, right? So we drew this in the voltage domain, but you can do the exact same thing in time, right? So if I told you, for example, that my nominal sampling position was there, right? But that due to jitter, there's some, and let me do that in a different color so you can actually see it. There's some distribution of jitter around that point, right? What you want to make sure is that you're always, let's say, below or before those points in terms of the sampling, where you're guaranteed to get a wrong answer, right? So all I'm saying here is that, if this equation implied that let's say your V margin needed to be, for example, 7 sigma of the noise to get 10 to the minus 12 bit error rate, I'm just saying the exact same thing, but here in the timing domain. All right, so if I told you that the sigma of the timing jitter was, let's say, whatever, x picoseconds, if I wanted to get a 10 to the minus 12 bit error rate, then I need to make sure that my timing margin is 7 times that x on one side. Is that more clear now, or? Yeah.
Although I guess technically if you go to the sides, then even your amplitude shrinks, so you have lesser space for the
Okay. So you're asking about the interaction between timing and voltage. You're absolutely correct. We'll handle that in 1 second. Okay, that's absolutely correct.
So we're assuming the voltage is flat.
Right. Okay. So one of the key things, which you guys have already caught on, which is good, is that indeed in this voltage timing budget, the interaction between voltage and time is largely ignored. Okay? Because basically I'm just sort of doing one budget on voltage and a completely separate budget on time. Right? And indeed that is an issue. Now, it turned out that, again, in these computer systems it was not so bad. Because notice I'm doing a lot of really, really worst case stuff. Right? So because of that I was sort of intrinsically pushed to have really large margins everywhere. And once I had really large margins, okay, even if I made some mistakes in my calculations, then, things would still sort of work. I'm just maybe being wasteful, right? But you're absolutely right. We haven't accounted for that yet, and that's one of, let's say, the main goals of this set of slides is to have to figure out how we'll really handle that. Okay? Okay, so that's kind of all there really is to timing jitter, except for just one thing, which I think, maybe confuses people when they first sort of think about it. So if you remember over here, sort of when we went through this example, we had to figure out how that voltage noise was actually filtered before we figured out what the final sigma squared going into our comparator was. Well, turns out jitter can get filtered the same way. Okay? Just for slightly, let's say, different reasons or slightly different mechanisms. Okay? But indeed, there are actually ways of filtering jitter out. So I've kind of mentioned a couple of them here, but let's see if intuitively you guys can sort of explain how could you create a quote-unquote filter on jitter. How could I basically take something, for example, that I transmitted and, there was some jitter on that transmitted pulse. How could I sort of filter out some of that jitter?
Your CDR loop is so nice, then you can track this timing variation as well.
Right, exactly. So let's imagine that magically my clock and data recovery loop is perfect. So as soon as I notice that there's jitter on the incoming data, I automatically move my clock sample to exactly compensate for that, right? Well, hey, guess what? I've quote-unquote filtered the jitter. In that case, I've actually canceled it, right? Now, the reality is no CDR loop can instantaneously track that jitter. And so instead what you do is you basically create some filter on that jitter, right? So some jitter components at, let's say, quote-unquote low frequencies, you'll actually be tracking. And others that are much faster than what your loop can track would basically be unattenuated, right? So indeed, if you actually look at it, in many sort of link specs or link, let's say, standards that you might work with, for example, PCI Express or ZOwie or any one of these other ones, a lot of times what people will do is define what's called a jitter tolerance mask, okay? So just to sort of give you an idea of what this really means is that basically what this plot here is sort of showing you is it's saying, okay, if I'm going to take your receiver, for example, what I want you to be able to do is tolerate a certain magnitude of sinusoidal jitter at a certain frequency. In other words, if I just add in that amount of jitter at that frequency, then I want to make sure that your link still works with a specified bit error rate. Okay? And again, by the way, just because you might hear it, sometimes people refer to sinusoidal jitter as SJ. Don't ask me why, but that's just people like to do those abbreviations. Okay? So as an example, if I look at this green curve here, what this mask is basically specifying is it's saying, if I put a jitter frequency of 22 kilohertz in, and jitter frequency means that sort of, my timing samples are jumping kind of back and forth with that sinusoidal frequency or sinusoidal shape and frequency. Right? If I tell you that I jitter your clock at 22 kilohertz with an amplitude of 8.5 UI, meaning 8.5 symbol periods, then I want your links to still work correctly. Okay? And by work correctly, what I mean by that is still have the same bit error rate that it used to have before. Okay? So similarly, as an example, if I took it up to, let's say, a megahertz of jitter frequency, then I would still say that I basically want you to tolerate up to about 1.5 UI of sinusoidal jitter without degrading the bit error rate. Okay? Does this sort of make sense to people just in terms of what the mask is specifying? Okay, so the way you can kind of think about this is that this mask is kind of telling you something about what the dynamics of your CDR loop need to be. Right? Because what this is kind of telling you is that if I'm going to put this big of an error signal in at this low frequency, then my CDR loop kind of needs to have a lot of gain to attenuate that big error signal in the time domain. Okay? This kind of make sense to people, or? Yeah.
So how do we really get this mask? What I mean is, without knowing the hardware we need to use.
Okay. So what really happens is some standards body sits down, and a bunch of people talk to each other, and either for technical reasons or non-technical reasons comes up with what they think the mask should be, based on maybe what they previously built or things like that. And then they say, okay, well, if we all use this mask, then now I can build a bigger budget and ensure that, our links will be able to talk to each other. But, by the way, this particular shape is a very common shape. And this basically comes from, and again, we'll talk about this more later, but this basically comes from assuming that the CDR looks something like it has an integration in the feedback path. So that at low frequencies, you really do have a lot of gain to basically counter these kinds of errors. So, Stephen, did you also have a question, or?
Yeah, well, I was wondering what sets that peak value. Like, how do they determine that you need to tolerate 8.5 rather than 10 UI or something?
Right. Okay. So again, this is largely related to sort of the, let's say, the budgeting that people do, right? So this could be something like, well, okay, imagine you have a crystal somewhere, right? And you know that that crystal over the long term can have a really big drift compared to some other crystal somewhere, right? So that 8.5 UI may just come from integrating out the drift of that crystal over some number or some potentially very large number of clock cycles. Right? So that's usually where something like that would come from. But again, you shouldn't take these, let's say, too seriously, in the sense that usually this mask is kind of derived, largely actually coming from what people know they can actually build. And therefore, what they'll usually do is drive the specs on the components to make sure that, sort of with that kind of mask, the entire system will actually work. All right, so you could say something like, okay, your crystal needs to have better than, X dBc per hertz at this frequency offset, because I know that my frequency mask looks like, my jitter tolerance mask looks like this, and so on and so forth. Does that make sense, or? Okay, other questions on this, or?
So if, for example, temperature were changing on some physical time scale, would that sort of be in this realm, or is that?
Yeah, well, probably for most systems, that's probably somewhere down over here, right? Because that's 22 kilohertz is already pretty fast for most temperature-related kind of stuff. So temperature, if you really have a CDR, usually temperature is not such a bad thing to deal with. If you have other types of systems where you just sort of once in a while figure out what the clock phase is supposed to be, then temperature tends to be a bigger issue, because it's all a question of just how big is the drift between the periods of time where you actually figure out what the right clock phase is supposed to be. Okay, so we've talked a lot about sort of how CDRs can actually filter jitter. Turns out there's even a more straightforward way that you can actually end up filtering some jitter. Okay, and so in order to see that, I just wanted to sort of walk through actually what's a fairly common case in many of the links that you might deal with, which is the so-called source synchronous systems. Okay, so just as a reminder, in source synchronous, what I'm basically doing is I'm taking a clock, I'm basically feeding it to the transmitter, so then I'm going to take that same clock, feed it over some link, and then use that clock to actually clock the receiver as well. Okay? Now, the only thing that I've changed from sort of the previous pictures that I showed you was that rather than taking that clock directly to clock the links, usually it's pretty tough to get a 10, 20 gigahertz kind of crystal. So instead what you'll do is you'll take a lower frequency crystal, and then on the chip you'll use a phase lock loop to actually multiply the frequency up. Okay? So here what I've done is I've actually taken that same sort of reference clock. I'm going to use a PLL or a phase lock loop on the transmitter to multiply it up to whatever the data rate is supposed to be. I'm going to forward that over to the receiver. And then at the receiver, I'm also going to use a phase lock loop to multiply it up to actually get my data samples. Okay? So my claim is that if you build this kind of system, and I looked at what was happening to the jitter from that crystal source, which, by the way, you'd like that crystal to probably be pretty cheap, which means it may actually have a lot of jitter. Turns out you're actually going to be doing some filtering on that as well. Okay? So what I wanted to do is just kind of quickly walk through this example to see what kind of filter do you actually end up applying to that jitter. Okay? So let's just sort of walk through this, let's say, piece by piece. So in the phase domain, or rather I should say, if I wanted to know what was the phase of the transmit sort of data, which, by the way, I've sort of annotated, that's showing up right here, as a function of my source phase. What are the sort of transfer functions that I'm going through here? How do I get from this source over to that data? What's the first thing I go through?
PLL.
Yeah, I go through the PLL, right? So that PLL, in case you haven't seen it before, that just has some transfer function associated with it. Okay? So, and by the way, I'm going to be annotating the transfer function of the transmit PLL differently than the receive PLL, because you'll see in 1 second, those differences are actually going to matter. Okay? So now what else do I do? And by the way, let's assume the transmitter itself is kind of perfect here. Right? So just whatever clock edge you feed it, that's kind of the clock edge that comes out of it. What else do I do?
There's a delay through the data
there's a delay through that transmission line, right? So in the S domain, how do I model that? Had somebody say it. Just speak up. Go ahead, speak up. You said the right thing.
E to the minus S top.
Yeah, so it's just going to be E to the minus S times whatever that delay is, right? And then that's going to be multiplied by whatever the source phase is in any case, right? Okay, so now, how about on the receiver? What's that going to be? What do I do on the receiver first? And again, let's assume this little, box here is ideal and has 0 delay and all that other good stuff. So how does the source, basically phase, arrive at the receiver? What is the filters that are applied to it?
delay through the channel than the PLL?
Yeah, so it's just going to be a delay through the channel. So I'm just going to reverse the order a little bit to make my life easy. So there's going to be a PLL at the receiver at the end of it. And then again, there's also going to be some delay through the channel. Right? Okay, so now if I want to know sort of, let's say, the effective phase that I'm getting, or rather the effective jitter, what do I have to do?
Subtract them.
Yeah, I just subtract the transmit from the receive, or vice versa, right? In other words, if I do phi tx of s minus phi rx of s, right? Then of course what I'm going to end up with is just basically the difference of those two transfer functions. Right? So I'm going to have the HPLL on the transmitter, then with the delay of the data, minus the PLL at the receiver, then also with its now different delay, then just times, of course, whatever the source phase was. Okay? So that whole thing in brackets I'm just going to call something like the jitter transfer function. And I'm just going to do this because I'm lazy to write, the phi source again. Okay, and I'm actually just going to rearrange this thing slightly in a way that may not immediately be obvious. But you'll see in 1 second why I've done this, because it's actually going to give us a good hint as to what the shape of this filter is going to look like. Okay? So the first thing I'm going to do is I'm just going to pull out the delay. I'm going to pull out the data delay. Okay? So if I do that, I can actually write things in a very interesting form. So first of all, what I'm going to get is something that looks like the difference between, a sample and a delayed version of the sample, then times the PLL's transfer function. Okay? And that's just going to be added to the difference between the two PLL's transfer functions. And, oh, sorry, I flipped that. That should be TX. And I just ran out of space, so that's that and that. Okay? Okay, so if you sort of look at this carefully, you'll see that if you redistribute the terms again, it'll all sort of, it'll all match with the previous equation. But the reason I did this is because, again, it's actually going to give us a hint as to what the shape of this transfer function really looks like. Okay? So notice the sort of two pieces here. So one piece is that I'm going to have the difference between the PLL transfer functions, right? And the other piece is that I have basically this sort of this delayed difference, or something like 1 minus z to the minus x, right, times this PLL transfer function. Okay? So actually, maybe just based on this, does anybody have an idea of, and let's maybe even just focus on this part of it first. What does this say about how you're going to be filtering out the jitter from the source? And in particular, what does this whole thing say about, for example, what you'll be doing to low frequency jitter?
It's a low pass filter.
What's a low pass filter?
The 1 minus e bar.
It's a high pass, right?
Ah, okay. So is the 1 minus a delay a low pass filter, or is it something else?
It's a high pass.
Yeah, it's actually a high pass, right? It actually kind of looks like a derivative, right? So in fact, if you look at that, and we're sort of almost out of time, but if you look at that, and I'll sketch this in more detail next time, but it actually looks something like this in the frequency domain. Okay? By the way, what is that peak value there for just the delay difference part? In other words, just for this 1 minus e to the minus s delta t. Yeah, it's a factor of 2, right? It's 6 dB. Right? Because basically if I do 1 minus minus 1, I get 2. Right? Okay, so indeed this piece right here is actually saying that as long as I'm at relatively low frequencies, where this difference in delay is kind of small compared to my frequency, then when I do A minus B, A and B kind of look the same, right? Because I haven't phase shifted them very much relative to each other. But if I get up to a frequency where that delay is comparable to my sort of period of the jitter, then at some point I might actually even amplify the amount of jitter that I have, right? Does this kind of make sense to people, or? Okay, so it turns out that a very similar effect happens here, because these PLLs tend to be low-pass filters. But if they're not exactly at the same frequency, in terms of their cutoff or their bandwidth, then what will happen is at low frequency, both of the PLLs will track. And so you just subtract out, the same thing would pass through both PLLs. But then when one of the PLLs start filtering and the other one does not, that's when you'd start actually passing some jitter through, right? Because one tracks, one doesn't. Finally, when both don't track anymore, then doesn't matter what you did, none of it gets through either one of the PLLs anyways. Okay? So this makes sense to people, or? Okay, so we'll sort of pick back up with the details of this next week. So just a reminder, no lecture on Thursday. So I'll see you guys in a week.